Hello everyone, and welcome to my code review for my warehouse inventory application developed as part of my Southern New Hampshire University CS 499 capstone project. In this walkthrough, I'll be analyzing the functionality and structure of my existing Android-based inventory application and discussing my plans to enhance it into a modern, full-stack web solution. The presentation will be divided into two major sections. The first half will cover the code review across three main categories: software design and engineering, algorithms and data structures, and databases. The second half will focus on the enhancement plan, where I'll describe how I intend to evolve this project by converting it into a mean, full stack application, implementing role based access control, and integrating camera based barcode or QR scanning. Let's begin with software design and engineering. The warehouse inventory application is an Android-based system designed to allow users to log in, view, add, edit, and delete inventory items. Its structure follows a traditional Android structure, with activities represented in the main user-facing components and an SQLite database managing data persistence. Let's start with mainActivity.java, which serves as the central hub of the application. This activity manages the primary user interface, specifically the grid layout that displays all the inventory items currently stored in the database. The onCreate method initializes the main layout, sets up the database helper instance, and populates the user interface by calling populate items. It also configures a floating action button that allows the user to navigate to the Add Item screen. The floating action button, or FAB, acts as a quick access control for adding new inventory items. When tapped, it triggers an intent to start the Add Item activity, allowing users to enter new data into the system. This approach provides a simple, intuitive way for users to expand their inventory and demonstrates effective use of Android's intent-based navigation system. The populate items method retrieves all stored items from the SQLite database and dynamically creates buttons for each item. Each button displays the item's name and quantity. When clicked, these buttons open the item detail activity, passing along the item's unique ID for reference. This function demonstrates dynamic UI generation. The interface updates automatically whenever the data changes. By calling this method in both onCreate and onResume, the grid refreshes after an item is added or modified, ensuring the displayed data is always current. While this design is straightforward and functional, it does reveal some opportunities for improvement. For example, creating and removing all views each time the grid updates can become inefficient as the dataset grows. A more scalable solution would use a recycler view, which is designed for dynamic lists and provides better performance in memory management. Additionally, the activity could benefit from separating the UI logic and the data retrieval logic into distinct layers, ideally using the MVVM or model view model pattern to improve maintainability and testing. Next, let's examine loginactivity.java. This file manages user authentication by collecting a username and password and then validating them against stored credentials in the database. The attempt login method here retrieves the input from the text fields, ensures both fields are filled, and queries the user table to check for a matching record. If a match is found, the user is granted access to the main inventory screen. Otherwise, an error message occurs. This implementation clearly handles the basic flow of user login. However, there are some aspects that could be improved for better security and error handling. Currently, passwords are stored in plain text, which poses a security risk. A future improvement would be to store hashed and salted passwords, ensuring that sensitive user data remains secure even if the database were compromised. Additionally, the code opens and closes a database connection directly from within the activity. Refactoring to use a repository pattern would separate concerns and improve maintainability by centralizing all database interactions in a single data layer. The new user activity.java handles registration. It allows new users to create an account by entering a username, password, and confirming their password. The code includes validation checks to ensure that the fields are filled and that both passwords match. Once validated, the application uses a helper function from database utils to check if the username already exists before creating a new record. This prevents duplicate accounts and maintains data integrity. Okay. This method, the register user method, demonstrates a solid workflow for adding new users but could be improved through additional input sanitation and exception handling. For example, it would be beneficial to catch potential database insertion errors and display more descriptive feedback messages to the user. In terms of structure, this activity follows best practices by using content values to package data for insertion, ensuring clean, readable code. However, consistent inline comments would help future developers understand each stage of the process more easily. Now, let's move on to the add item activity.java. This activity enables users to enter the name and quantity of the new items to add to the inventory database. It includes validation checks to ensure that both fields are filled and that the quantity is a valid number. Upon successful entry, the application inserts the data into the items table and displays a toast notification confirming that the item was added. Looking at the add item to database, the logic here is clean and easy to follow. However, like the other activities, this code could benefit from more robust error handling. For instance, catching SQL exceptions or handling unexpected null values gracefully. Additionally, database write operations like this could eventually be moved into an asynchronous background thread to prevent potential UI freezing, especially as the dataset grows larger. Finally, the last one we have within this category is the item detail activity.java. This file manages the display and modification of individual inventory items. When opened, it retrieves the item's details by ID and populates editable fields for the name and quantity. The user can then update or delete the item, with both actions directly affecting the database. It provides a clear example of full CRUD operations: create, read, update, and delete, all integrated into a user-friendly interface. The update and delete logic are well implemented but could be strengthened through more detailed user feedback and exception handling. For instance, confirming deletions through a dialog box would reduce accidental data loss, and wrapping the database operations in a try-catch block would make the code more resilient to runtime errors. Additionally, separating the database logic into helper classes or service layers would improve maintainability and make the code base easier to extend. For example, if more complex item attributes were added later on. Overall, from a software design and engineering standpoint, the current code base demonstrates clear functionality, logical flow, and user-friendly navigation. Each activity is responsible for a specific part of the user experience, and the design pattern is consistent throughout the application. However, there are opportunities to enhance this project's architecture for scalability, efficiency, and security. Implementing design patterns such as the MVVM, model view model discussed above, or the repository pattern, improving input data validation, and adding comprehensive error handling would elevate this project from a functional prototype to a professional grade application. Furthermore, inline comments could be placed throughout to allow future programmers to better understand the code base and the developer's intentions. Now that we've reviewed the program's overall structure and software design, let's move into the second category, algorithms and data structures. In this section, I'll focus on how the application's logic controls data flow, how data is organized and validated, and how simple algorithms are used to maintain accurate system behavior. Let's begin with item.java, which defines the data structure representing a single inventory item. This class encapsulates three fields: an integer ID, a string name, and an integer quantity. It includes a constructor to initialize these values, getter methods to access them, and a setter for modifying the quantity. This is a straightforward example of object-oriented encapsulation, ensuring that each item is treated as a discrete, well-defined object. It provides a foundation for data consistency throughout the application. Every operation on inventory items interacts with these standardized fields. The constructor ensures that each item object contains valid data at creation time, while the getters and setters support controlled access. Although this is a simple structure, it demonstrates a key principle of data abstraction, shielding other parts of the program from needing to know the underlying details of the item's implementation. A small area for improvement here would be to add basic validation within the setter, preventing invalid quantities such as negative numbers from being assigned. This would strengthen the data integrity of the application at the object level. Now, moving back to the main activity, the populate items method demonstrates one of the most important algorithmic processes in this application, iterating over a dataset to dynamically generate UI elements. In this method, the application retrieves a list of all items from the database using the helper class, then loops through the list to create a new button for each one. Each button's label displays the item name and quantity, and each is configured to open the detailed view for that specific item when clicked. This approach dynamically reflects the current database state, meaning the interface is automatically regenerated whenever items are added, updated, or deleted. From an algorithmic standpoint, this loop, shown on line 65, efficiently maps data objects to interactive components. However, since it rebuilds the entire grid on every refresh, it isn't the most efficient design for larger inventories. A more advanced approach would be to use the recycler view adapter pattern, which only updates the specific elements for that change, improving time and memory complexity from ON full redraws to a more scalable event-driven model. Beyond dynamic UI generation, the application employs several smaller algorithms focused on input validation and conditional flow control. These are found primarily in the login, registration, and item creation activities. In the login activity.java, the attempt login method on line 46 is a good example of procedural logic and branching conditions. Here, the code first validates that both username and password fields contain text. If either is empty, it terminates early and displays a message to the user. If both fields are filled, it constructs an SQL query that checks whether a record with the matching username and password exists in the user table. This structure represents a simple decision-making algorithm. Step 1, validate the input. Step 2, execute the query. Step 3, check the results and take an appropriate action. It's straightforward and effective, ensuring the application responds immediately to invalid input and preventing unnecessary database operations. The toast messages provide user feedback after each decision point, a good practice for the user experience. However, this method could be strengthened by adding try-catch blocks around the database query to handle potential SQL exceptions or null pointer errors. This would make the algorithm more robust, especially in edge cases like corrupted data or connection interruptions. Next, let's examine another key algorithm within the new user activity, the user registration process. This function combines multiple conditional checks and database logic to ensure new users are added securely and correctly. The logic here can be broken down into three main decision steps: input validation, confirm all the fields are filled and both passwords match; uniqueness check, query the database using the database utils.usernameExists method to ensure that the username isn't already taken; database insertion, if all checks pass, insert the new user record. The database utils class supports this logic with a helper method that queries the database for an existing username. It returns a Boolean value, true if the username exists and false otherwise. This allows the registration algorithm to make a clean, binary decision before attempting to insert a new user. This is a simple yet effective example of a function-level abstraction, packaging a reusable query into its own utility class to promote clean, modular code. Taken together, the login and registration workflows demonstrate how decision-making algorithms and validation routines are integrated throughout the application. While they are not computationally complex, they play a critical role in ensuring logical consistency, user data integrity, and predictable behavior. In a future enhancement, these routines could be expanded to include more advanced validation algorithms, such as regular expression matching for username and password complexity, or input sanitation functions to prevent potential injection attacks. Now, let's turn to the algorithm used in add item activity. This function follows a procedural pattern similar to the user registration logic. It begins by checking that both the name and quantity fields contain data. If they do, it then attempts to parse the quantity as an integer. If parsing fails due to invalid input, the method terminates early and displays an error message. If all checks pass, the method proceeds to insert the data into the database and display a confirmation message to the user. This control flow is linear and efficient, preventing invalid data from ever reaching the database layer. From an algorithmic perspective, this method could be slightly enhanced with an exception handling that logs errors rather than relying solely on toasts for user feedback. For example, adding structured logging would provide a way to diagnose input errors more effectively during development or maintenance. Additionally, input parsing could be improved through a reusable utility class that validates and converts text fields consistently across the entire application. Finally, the item detail activity contains two essential algorithms, one for updating items and one for deleting them. Both are examples of conditional data manipulation based on user input. The update algorithm retrieves text from the input fields, validates it, and executes an SQL update command if the data is valid. Similarly, the delete algorithm executes a delete command based on the item's unique ID. Both of these routines are simple but demonstrate good use of parameterized SQL statements, which prevent SQL injection vulnerabilities. However, each could be further optimized through reusable database service methods, abstracting the CRUD operations so activities focus on business logic rather than SQL syntax. This would simplify maintenance and make future migrations to a new database system, such as MongoDB, much easier. In summary, the warehouse inventory application demonstrates consistent use of logical decision-making and basic data structures. Although the algorithms are relatively simple, they effectively control program flow, validate user input, and manage data interactions. Areas for improvement include adding exception handling, enhancing validation logic, and refactoring repetitive code into shared utility classes for greater efficiency and maintainability. From a computer science perspective, this section of the project demonstrates an understanding of algorithmic design fundamentals, structured data representation, and procedural logic, all applied in a practical, real-world software context. Now let's move into Category 3, Databases. This section examines how the warehouse inventory application stores and manages its data using SQLite, focusing on schema design, CRUD operations, and opportunities for optimization and security improvements. We'll begin with appdatabasehelper.java, the class that forms the foundation of the application's data layer. This file extends SQLite Open Helper, meaning it controls database creation, version management, and the execution of SQL statements. Inside this helper, the database is defined as app_data.db with a version number of 1. Two primary tables are created here, the users table and the items table. The users table stores authentication information, an auto-incrementing ID, a username, and a password. The items table stores inventory data, again with an auto-incrementing ID, a name, and a quantity column. Each SQL statement follows good practice by explicitly naming columns and defining data types. However, the design could be strengthened by enforcing additional constraints. For example, declaring the username column as unique and adding not null checks where appropriate. In future iterations, these constraints could help catch duplicate data earlier and reduce reliance on manual validation in the application logic. The onCreate method on line 49 executes both create table statements to build the schema when the application first launches. By overriding onUpdate, the application can also handle schema changes between database versions by dropping the old tables and recreating them. While this is a common approach for small applications, it does mean data is lost whenever a schema change occurs. A more mature solution would involve writing custom migration scripts to preserve existing data when tables change. Next, the getAllItems method is used to retrieve the entire list of items from the database. It opens a readable database connection, runs a query on the items table, and loops through the results with a cursor object. Each row is converted into an item object, which is then added to a list that gets returned to the caller. This is a great example of data mapping, converting raw SQL results into structured objects that can be used throughout the application. However, the method currently closes the database connection after each read. While this is safe for preventing resource leaks, it may impact performance under frequent calls. Using a singleton database instance or a connection pool would improve efficiency in larger applications. This loop is simple and effective, iterating over the result set to extract each item's ID, name, and quantity. The use of getColumnIndex or throw ensures that any mismatched column names will throw an exception, helping detect schema issues early during testing. To make this more resilient, it could include a try finally block around the cursor and database operations to guarantee resources are closed properly, even if an exception occurs. The add item method handles the create portion of CRUD. It uses content values to structure the data and then inserts a new row into the items table. If the insertion returns a positive row ID, it's considered successful. This is a clean implementation, but the method could benefit from validation to ensure that the same item name isn't added twice accidentally. This could be enforced either through application level checks or by adding a unique constraint to the database schema. The getItemById method implements the read portion of CRUD for a specific record. It queries the database for a row matching the provided item ID and returns the corresponding item object. This method demonstrates good use of parameterized queries, which helps to protect against SQL injection. It's a strong practice for security, and it could be applied consistently throughout the application for all SQL operations. Next, let's take a look at itemContract.java, which defines the database schema in a centralized manner. This file provides constraints for the table name and column names, ensuring that the same identifiers are used consistently across all queries. This is a great example of maintainable database design. If the column names ever change, only this file needs to be updated, reducing the risk of errors throughout the code base. The database utils class adds a layer of utility for database operations that don't fit neatly within the helper. In this case, it provides a single method, username exists, which checks whether a given username already exists in the user table. This is a simple Boolean query that returns true if the cursor count is greater than 0. It's efficient and reusable, showing good coding discipline by abstracting repeating logic into a shared function. Overall, the database layer of the warehouse inventory application is well structured and functional. It follows clear CRUD principles and demonstrates good encapsulation between the UI and data storage layers. However, there are a few key areas where database implementation could be strengthened. Number 1, security. Currently, the user passwords are stored in plain text. A major enhancement would be to use hashed and salted passwords, for example, with SHA-256 or bcrypt to protect credentials. Number 2, error handling. Adding try-catch blocks around database access would improve stability and diagnostics. Number 3, efficiency. Using a singleton database helper or connection pool would minimize resource overhead. Number 4, schema evolution. Implementing database migrations would preserve data across version updates. In summary, the database code demonstrates a strong understanding of SQL operations and Android data management principles. It is both functional and logically sound, but can be enhanced with more robust security, error handling, and optimization for scalability. This category also ties directly to the next phase of the project, migrating to a NoSQL database within the mean stack, which I'll cover in the enhancement plan portion of this presentation. Now that I've completed the code review portion, I'll move on to the enhancement plan section. Here, I'll explain how I plan to evolve the warehouse inventory application into a more modern full-stack web application. The first major enhancement is migrating the existing Android-based project to a mean stack architecture that's MongoDB, Express, Angular, and Node.js. In the current Android implementation, most of the logic, including the UI, data retrieval, and database interaction, exists inside activities. This tightly couples the user interface with the business logic, which makes maintenance and scalability more difficult. The mean stack redesign addresses this issue by separating the system into 3 independent layers. Angular will handle the front-end interface, delivering a responsive, web-based user experience. Node.js and Express will form the back-end server, hosting APIs that manage authentication, item management, and role permissions. MongoDB will serve as the database, storing user and inventory data in a flexible, document-based format. This layered architecture enforces separation of concerns, where each component handles one primary responsibility. For example, Angular will render the inventory grid and communicate with the backend through RESTful API calls rather than direct database access. This structure also enables easier scaling and cross-platform access. Users will be able to manage their inventory through a web browser on any device, not just an Android phone. From a software engineering perspective, this enhancement demonstrates the ability to design and implement modular systems using asynchronous data communication. The use of HTTP requests and JSON payloads will replace direct SQL calls, allowing the front end and back end to evolve independently over time. Additionally, this transition allows me to implement unit and integration testing for each part of the stack. Angular components can be tested using Jasmine and Karma, while backend routes and logic can be tested with frameworks like Mocha or Jest. Through this enhancement, I'll demonstrate several core technical skills. Building RESTful APIs using Express and Node.js, implementing CRUD operations through asynchronous service calls, designing Angular components that interact with API endpoints, configuring and securing a MongoDB database for persistent data storage, deploying and managing a full-stack environment suitable for real-world use. Each of these skills supports key course outcomes in the software design and engineering and professional practice, showing that I can design scalable, maintainable software solutions using industry standard tools and frameworks. The second major enhancement I plan to implement is Role-Based Access Control, or RBAC. This addition will allow me to assign permissions to users based on their roles and responsibilities within the system, ensuring that each user can only access the data and functionality appropriate for their level of authorization. Currently, the warehouse inventory application treats all users equally. Once a person logs in, they have full access to view, modify, and delete items. While this works for a small prototype, it poses significant risks in a production environment. By introducing RBAC, I'll align the system with modern security standards and the principle of least privilege. In the existing Android version, user authentication is handled directly through a query in the login activity. Every verified user gains access to the same interface and capabilities. In the enhanced system, authentication will still verify credentials, but authorization will go a step further, checking what the user is allowed to do. For instance, a manager will have full control, including adding and deleting items. A standard user might only be able to add or view items, as well as increment or decrement their quantity, while a viewer role would be restricted to a read-only access. On the back end, this functionality will be implemented using Express middleware. Middleware in Express allows for logic to run between an HTTP request and its final route handler, making it ideal for access control. Each protected route, for example, API items delete or API users manage, will have an authorization middleware that checks whether the authenticated user's role allows access to that endpoint. If not, the server will immediately return a 403 forbidden response. From a design standpoint, RBAC can be thought of as a small but powerful algorithm layered into the API logic. Each route request triggers a sequence of checks. Number one, the authentication check. Verify that the user's identity is valid using a JSON Web Token, JWT. Number two, role extraction. Decode the token to identify the user's assigned role. Number three, permission validation. Compare the role's permission set against the route's required privilege level. Number four, decision outcome. Grant access if permissions match, otherwise deny. This sequence ensures that access decisions are made consistently and efficiently, protecting sensitive operations and maintaining system integrity. The key benefits of adding role-based access control include security, as it reduces the risk of unauthorized access or accidental data modification; scalability, new roles and permissions can be added without rewriting core logic; maintainability, centralized control over permissions simplifies auditing and updates. Implementing role-based access control also demonstrates an understanding of security design patterns and algorithmic thinking, since it requires carefully structured data and logical decision-making to enforce permissions correctly. In terms of data structures, I'll use nested JSON objects or mongoose schemas in MongoDB to define roles and their corresponding permissions. Each user record in MongoDB will include a role field referencing one of these configurations. When a request is made, the middleware retrieves the role definition, checks the requested action, and compares it against the allowed permissions array. This creates a lightweight, scalable way to enforce permissions dynamically without hard-coding access logic throughout the code base. Beyond improving security, this enhancement also lays the groundwork for future extensions, such as an audit logging system that records when users modify data. That would provide traceability and accountability, both essential for any enterprise-level inventory management platform. The role-based access control enhancement directly supports the following course outcomes: algorithms and data structures. It applies logical decision-making structures to manage access and efficient data representation for role and permission mapping. Security. It enforces the least privilege principle and integrates secure authorization workflows. Software design and engineering. It demonstrates modular system design through middleware integration and separation of authentication from business logic. Together, these improvements make the application not only more secure, but also more professional and ready for real-world deployment. The third major enhancement I plan to implement focuses on improving the efficiency of inventory management by integrating camera-based scanning functionality. This feature will allow users to scan barcodes or QR codes directly from their device's camera, automatically importing or updating inventory information in the database. Right now, the process of adding items requires manual data entry. Users must type the name and quantity of each item, which is practical for small inventories but inefficient for larger warehouses or retail environments. Manual entry also increases the likelihood of human error, misspelled product names, or incorrect quantities. The barcode and or the QR code enhancement automates this process. Instead of typing, users can use their device camera to scan an item code, and the application will immediately fetch or register that item in the database. In the new mean architecture, this functionality will be implemented in the Angular front end using a JavaScript library such as zxing or Quagga.js. These libraries provide browser-based access to camera feeds and real-time image processing to detect and decode barcodes or QR codes. Once a code is successfully scanned, the application will send the decoded data to the Node.js backend via a RESTful API call. The backend will then check MongoDB to determine whether the item already exists. If it does, the record will be retrieved and displayed on the screen. If it does not, a new item document can be created automatically, with the user prompted to fill in any missing details such as quantity or description, or a message can be displayed to the user indicating that the item is not in the database. From a technical perspective, this feature demonstrates the integration of hardware capabilities with web-based applications. It involves handling asynchronous operations, capturing video input, processing it for barcode patterns, and sending API requests in real time. Proper error handling is crucial here. If the camera is not accessible or the scan fails, the app will display clear feedback and allow the user to retry without reloading the page. Let's briefly outline the data flow for this enhancement. The user opens the Add Items screen in the Angular front end. They select the Scan Barcode option, activating the camera through the browser's media API. zxing detects the barcode and decodes its value. That value is sent as JSON to the Express API. The backend queries MongoDB for a matching record. If found, it returns the item data. If not, it creates the new document and returns a success response or indicates to the user that the item is not in the database. Finally, the Angular UI updates to reflect the new or retrieved item. This workflow is fast, reliable, and user-friendly. It transforms what was a manual input process into an automated, scalable operation that can handle thousands of items with minimal human error. On the database side, MongoDB's document-based design is particularly well suited for this kind of operation. Each item document can store fields such as the barcode value, product name, quantity, and timestamp of last scan. This flexibility makes it easy to add new attributes later, for example, supplier data or storage location, without altering the schema structure. The API layer will also include input sanitation to ensure malicious or corrupted data cannot be inserted into the database. Even though barcode data is often numeric or alphanumeric, it is important to validate it before storing to maintain data integrity. This enhancement demonstrates skills in several key technical areas. Integrating multimedia APIs and hardware features with web applications, implementing asynchronous data flow between front end and back end, designing API endpoints for real time data processing and database interaction, ensuring secure data handling and input validation, and building a responsive UI that reacts to live input and system feedback. Together, these skills align with the course outcomes of software design and engineering, databases, and security, demonstrating practical integration of hardware, software, and data management concepts in a realistic development context. From an end user perspective, the benefits are significant. The scanning feature reduces manual workload, improves accuracy, and saves time during inventory updates. For example, warehouse employees can walk through storage aisles, scan product codes, and instantly update stock quantities without touching a keyboard. This functionality brings the warehouse inventory application closer to the performance and convenience expected in a modern inventory management system. To summarize the enhancement plan so far, the mean stack migration modernizes the architecture and introduces scalability. Role-based access control adds security and enforces least privilege principle. Barcode and or QR code scanning improves efficiency and user experience. Together, these enhancements transform the warehouse inventory application from a functional mobile prototype into a robust, full stack system ready for real world deployment. That brings us to the conclusion of this presentation. In the code review, I analyzed the existing Android application across three categories: software design and engineering, algorithms and data structures, and databases. Each category showed solid foundations but also opportunities for growth in areas like modularity, error handling, and security. In the enhancement plan, I outlined a clear path forward to address those limitations through the adoption of modern web technologies, secure design principles, and automation. These improvements not only enhance the application's functionality, but also demonstrate advanced software engineering skills aligned with the core learning objectives of the computer science capstone course. By re-engineering the warehouse inventory application into a mean stack system, adding role-based access control, and integrating barcode scanning, this project will serve as a comprehensive example of design evolution. From localized mobile app to a scalable, secure, and efficient web-based inventory solution. Thank you for watching this presentation on the warehouse inventory application. This concludes my code review and enhancements plan for the computer science capstone project.